the computer podium. So this is I prepared a presentation to introduce you and give an overview to the course. Okay, so let's see, there must be a stick somewhere. Okay. Next time, this is fine. But okay, when you get into Sakai, e-learning, and go to the course, EML 4313, spring 2015, this is what you would see more or less. Okay, so on the left here column, there's a few buttons that you are very familiar with. Some you're not. The course reserves is one that I'd like to mention. If you go into the portal, which I will mention later, and then go from there, you can get to the syllabus and look at. I think the course contents. I listed 2 books. One is Crazy, and the other is this one, Craig and Cordilla 2006 Structural Dynamics. I recommend these books in case you need some books to read as reference to provide additional information, but you're not required to buy these books. It's up to you. Okay. My lecture notes should be sufficient, and like I said, it's up to the individual, because sometimes you may need to read additional material, so those are the reference. Now this book is reserved. That means that you can borrow from the library for 2 hours, maybe sit in the library to read. It's being ordered by the library, but you don't need the book right now. Like I said, my lecture notes should be sufficient. Now the resources is where the TA will post the best solutions and best reports for everyone to look at and to emulate. The TA for this course is Michael, who's sitting here. Michael took my IEA course last semester and was among the top students. At least 5%, top 5%. Okay. There will be also another TA, but will be more of a secondary nature to Michael, helping out Michael. He's also an excellent student, but he's helping with the finite element course that I'm teaching in parallel with this course. So Adrian is the main TA for the other course. Piazza. How many of you heard of Piazza or have used Piazza? Right, Dave is one. So this is very useful, and for the following reason. You can use Piazza to pose critical thinking questions, things that you are having in mind, and when you type on Piazza, essentially you address to the class. And Michael and I will monitor Piazza. Now the critical thinking questions, that's why it's called critical thinking, because it helps to improve the understanding of the material, of the concepts that are taught. And Sam, please work on the microphone.
Yeah.
This is a large class.
Yeah, no, I got you. I'll take care of it.
I have the Shure microphone here, but I'm not sure whether it's...
Yeah, I have to install some equipment for it all to work for you.
Okay, because Chad said that it was in the other room, it was the new system.
Bartram is going to be I have to reprogram it and do a bunch of things, but it'll be working for you if that's what you need.
Thank you, Sam.
Mm-hmm.
So please bear with me. I will have a microphone so that my voice will be louder. I speak softly, so I need a microphone. Now the second point is to provide discussions and answers to the critical thinking questions. And that makes the class more lively, okay? And as an incentive to doing so, you would receive active learning credits. The active learning credits will help your final course grade. Okay. So use Piazza to pose critical thinking questions, discuss answers, and receive active learning credits. So that's but there are other modes of posing critical thinking questions as well. In class is the preferred mode. I prefer that because that's lively, it's interactive, and that's the best method, I think. But you can also pose the CTQs or critical thinking questions in the team lecture summaries at the end of each lecture. I will form teams, and you will work with your team to write the lecture summary at the end, and you can write your questions in these team lecture summaries. You can talk to me after class and follow up with emails to remind me. Or you can use the continuous anonymous feedback to ask questions. Okay, I will create the Google survey and will post a link. Now the goals of the critical thinking questions and discussions in class is to develop a true understanding of the concepts taught and not memorization. And also, more importantly, is to create a vibrant and enjoyable two-way interaction for the class and for me, instead of the boring one-way lecture. I don't like the one-way lecture. I hope you prefer the two-way interaction. So please keep that in mind. Oh, one more thing. The active learning credit in the last semester, in fall 2014, the top student in the class actually received the final course grade above 100 because I added the active learning credit after I computed the final course grade. So the active learning credit is like extra credits. So I gave usually 0.1 point for each critical thinking questions or participation, answering discussion that help improve the understanding of the class. Okay. So that's, if you do 10 times, if you participated 10 times, that's 1 point, right? And that may make a difference in changing the course letter grade, bringing your course letter grade up by 1 notch. So keep that in mind. So, and here is the portal. So when you get into Sakai, you would see this link. This is the gateway to all of the documents in the course. Okay, syllabus, contents, policy, reports, exam, and so on and so forth. Please read these documents carefully. There's a list of topics. That's all the topics you want to learn from this course. This is written as fall 2014, and I will follow closely my version of fall 2014. Okay, that was the 4th time that I taught this course. This is the 5th time. And each time I teach, there was a different version. You can go back and see. And so if you look at that list, it's very detailed. I call it a book index because it functions like a book index because it has my lecture notes in PDF that I typeset myself. And you have a list of the topics within each set of lecture notes. So if you look at the topic, you have the corresponding lecture notes. Okay, if you search for a topic in the document. There's a weekly schedule, and this is the daily lecture summary, day by day. So I really advise you to follow the daily lecture summary very closely. Look at it at least once or twice a day. And then there are other things. One thing that I'd like to mention quickly is the integrated product and process design. That's a 2-semester course sequence that replaces your capstone design and 1 elective course. But I'll mention more maybe in the next lecture or in the 3rd lecture, because today we had to fix the computer podium, so I'd like to move on here. So the course contents, there's a link in the portal, so please look at that, because in that page you will see map out a temporary weekly schedule. But there's a more detailed weekly schedule from the fall 2014 semester, last semester, that you can look at, because like I said, for this 5th time, I want to follow closely the fall 2014 version of my course. That also help you because you can look at the detailed, well, all of the documents from fall 2014 is available to you, including the videos, the lecture videos. You can see my lecture from last semester and my handwriting, everything, right? So available. So if you, for fast students, if you want to learn ahead, you can go ahead and get ahead of the class. Essentially, I divide the semester into 2 parts. The first half of the semester and the second half of the semester. The first half of the semester will focus on linear second order ODEs. I think Sam, yeah, you can. Thank you very much. Yeah, thank you. Now, for scalar linear second order ODE, that's a prerequisite. That's what you should have seen in differential equations. So I will discuss these topics as extra lectures. Extra lectures means not the regular lecture during the week, but usually on Tuesday and Thursday, and I have created lecture videos that you can view to review. In class, I focus on the multiple degrees of freedom system, okay, meaning systems of ODEs instead of scalar ODEs. So these are coupled linear second order ODEs, and we go through generalized eigenvalue problem and then method to uncouple these ODEs and go back to the scalar linear second order ODE, okay, and then go through model equation, model superposition. Now, you know, this is essentially, let me ask you this question first. How many of you took vibration? One. How many of you are taking vibration in parallel with this course? One. So, meaning that the vast majority will take vibration. And you know, this first half of the semester is essentially the second half of vibration. So if you understand the material in this course, vibration will be a piece of cake. Okay? And when I taught in spring 2014, I was waiting in the corridor. It was in this room. I talked to a student who took this course, IEA, with another instructor, and he told me that he couldn't connect the content of this course to applications, engineering applications. So, you know, I told my class in fall 2014, and I repeat here, I don't want to teach math for engineering students, but I want to teach an engineering course with mathematics as a fundamental tool. So the primary goal is always engineering application. You can see here, motivation 1. I show you a real world application, the longest suspension bridge in the world, the Akashi Keiko Bridge, and connect you to what you learn in this course. Okay? The method that you learn in this course is applicable to real world engineering. Okay? Even though we simplify the problem, but the method is the same. Okay? I'll repeat that more and more, you will see. And so the key concept to remember is dynamics, vibration, periodic excitation, damping. In the second half of the semester, I just want to mention briefly here, okay? Because there's still more time and we'll come back to this. It's on Fourier analysis, Fourier series, function projection, but the important thing is this one, arbitrary excitation. You know, even if you take vibration course, I don't think this topic would be taught because it's advanced. And what it means is that if you take, let's say a bridge, a building, an airplane, a car, a train, a satellite, you know, these are all mechanical systems, right? And you excite with of force. Usually in differential equations or in other courses, you have very simple excitation, right? All of you took differential equations. Let's begin with a critical thinking question. Could someone in the class give an example of an excitation that you took, that you were taught, either in differential equations or in any other courses that involved linear second order ODEs? Do you remember? What type of functions did you encounter? Somebody, come on. Let's begin with interaction here. And remember, please remind me. I have not formed team yet. When I form team, I will be able to identify specifically. So if you contribute now, please send me an email so I remember your name. Go ahead, please.
So like a dampening spring?
Damping spring. I'm talking about excitation.
Right.
Excitation. Excitation means apply loading. Right? So what kind of applied loading did you encounter in differential equations? Very simple function, right? Linear function, perhaps sine, cosine, but not. Let me see whether I can bring up my. This is the way I write in class, and so I can produce PDF. I usually add annotation and post what I wrote in class for all of you. Let's see. Here I already prepared. So suppose that you have so this is let's say plane, the coordinate system. Must be a slide. That's this, so you can think of this axis. I think I need to turn off the small thing here. Now, this is another problem, you know, when I try to write on the axis, the ink appeared here, so that's due to the misalignment. So I need to get the classroom support people to help. But you know, since I'm not able to write, I will write after class and will post lecture. So think of this as a function. This is completely arbitrary, impossible based on prior knowledge that you get from differential equation to solve this. But in this course, you will learn to solve vibration problems excited by arbitrary function like this. And the reason is projection. And let me go back to my presentation slide here. I will link this slide in the slides in the daily summary. Oh, by the way, one more thing. 5 minutes before the end of class, could someone give me the timeout signal? You know, this clock doesn't work. Okay, so that I get you out on time. Okay, so this, what I just said, was a motivation for projection, function projection, because you can project any arbitrary function on basis of functions. Okay, and there are two important function bases that we talk about, the polynomial basis and the Fourier basis. polynomials is like a 1 t, t square, and so on and so forth. This is unfortunate, but Sam left. So you know, this is not easy to write. You see, when it's not exactly on the position of the stylus. It's so. For some reason, the other. Somehow I cannot bring up this. Oh, maybe it's here. Okay, so I need to guess, you know, where I should write so to get what I wanted. 1 t t square, and so on and so forth. TQ. So this is not optimal. This is TQ. Could someone remind the class of a very important series, power series that you have seen many years ago? What was your name?
Robin.
Robin. Robin. Okay. Would someone in the class say something? Yes.
Taylor series.
Sorry.
Taylor series.
You need to speak louder. Yes.
Taylor series.
Taylor series. Very good. What's your name?
Parker.
Parker. First name Parker. So Parker, Robin. You know, you will see that I will learn. You know, in the previous semester there were more than 100 students, and I know a lot of names. You will see. I will know many names of the students in class here. So Parker said Taylor series. Taylor series is an example, a classic example of power series. Okay. So once you can project an arbitrary function on the basis of polynomials 1 t, t square, t cube, you can solve you know, the linear second order ODE excited by arbitrary functions. That's very important. Because in real world problem, you don't always have simple functions like t squared, right, or sine, cosine. So talking about sine, cosine, that's an example of the Fourier basis functions. The motivation, real world motivation for the second half of the semester is, I'm very excited about this. I started last semester, and you know the Beatles, I'm sure everyone knows the Beatles, has a song named A Hard Day's Night. And that song has a very, very famous characteristic in that the opening chord, okay, the opening chord of A Hard Day's Night is not scored in music score, but it is really represented the whole era of rock and roll. And many musicians tried to replicate the chord and came up with many different versions. Okay, and in 2004, that's 40 years, when after the release of A Hard Day's Night in 1964, a mathematician used FFT, fast Fourier transform. Okay, that's a more advanced level in Fourier analysis, to analyze the sound recording of the opening chord of A Hard Day's Night and detect the musical notes in that opening chord. Okay, so you will learn in this course this real-world application, the use of FFT to detect, at least retrace the step of that mathematician. Now, you know, 2014, that's 50 years, you know, after the release of A Hard Day's Night. And if you go to the web, there's still heated debates on how to play the opening chord. You know, so you see that's how important that is. And there's another motivating document, that's Richard Feynman and piano tuning. I'm sure everyone of you know who Richard Feynman was. And not only that he was a brilliant physicist, but if you read this paper, you see that he understands deeply about the physics of the piano. Okay, so that's coming in the second half of the semester. And so this is the section 08. This is to give you an overview and the connection among different courses. Right? Static dynamics, you know all that. Now this is intermediate engineering analysis, and its position relative to the other courses. All of you took numerical methods, right? Because that's the prerequisite for this course. I should have put that above intermediate engineering analysis. But the knowledge of IEA will help in your vibration, which I mentioned before, and also in finite element analysis. Okay? And there are more that I will not talk about. This is more in my finite element version. And as real world motivation, I mentioned the Akashi chemical bridge, but also the discovery of Neptune. I have lecture videos that you can look at that, because that is more related to the scalar linear second order ODEs. Okay? It's extra lectures. Now this is section 0B, which you can also access in the from the portal, from the daily summary. Let's see. Okay, we still have some time. Okay. So let me go over that. We finish at 2:45. Okay. Select the default program. Sumatra PDF. It's a very nice small program that can read many different formats, including PDF and Deja Vu. And so I really suggest you install this, because then if you look at my courses where I use the Deja Vu format, you can read the lecture notes. Here, it's PDF. All right, yes. So here is the, let me see. Should be able to write with the stylus, but I need the classroom support to have some. So here I'm going to wave my hands to talk. Let's see, how do I hide this? Okay, so this is the course roadmap for scalar linear second order ODEs. Essentially, in general, it's a review, except you would learn new things. For example, I mentioned general excitation, right? And that you can do projection, and you get to power series or Fourier series, and that allows you to solve the single degree of freedom system vibration for any arbitrary excitation, right? And I did mention there, Taylor series is a particular case of power series. Okay, so that's why there's an arrow there. And you will learn about linear algebra of vectors but generalized to functions. For example, what does it mean two functions being orthogonal to each other? You know, with two vectors, you know what orthogonality, right? That's 90 degrees. But what is 90 degrees for two functions? And so that's more abstract there. Okay. and then there are more. But for the first half of the semester, that's this part. Okay, the first part was a review in the extra lectures. You have my lecture notes and lecture videos that you can view at home. In class, we focus on systems of coupled linear second order ODEs. Okay. By the way, I need to introduce the acronym of that. Linear second order ODEs. CC stands for constant coefficients, with constant coefficients. When you go to more advanced level, the coefficients need not be constant. You know, they can be functions. So that's why, to be precise, that's the acronym that we see often. You know, because it's a long, mouthful terminology. So having the acronym would be much faster and shorter. So there are many applications because single degree of freedom is too simple. You know, any real world application from, like I mentioned, bridges, buildings, cars, airplanes, satellites. These are all multiple degrees of freedom system. When you analyze real world problem, you can get to millions of equations, okay? Coupled equations. In this course, we deal with simpler system with only two equations, okay? But coupled. But the same method applies to when you have millions of equations. Okay? That's what you want to keep in mind. Many applications, vibration, circuits. And here, the important point is the generalized eigenvalue problem, how to solve generalized eigenvalue problem, what's the orthogonality among the eigenvectors, and how you project the system. You know, the goal is to make the problem simpler to solve, right? How do you do that? Caesar said more than 2,000 years ago. How do you conquer? What did Caesar say? Contributions? Divide and conquer. Right? You have a very complex problem, divide out into simpler problems and conquer. This is an example. You have a very complex problem, you don't know how to solve even with two equations now. But in this course, you will learn to divide and conquer. And the division into simpler problems is through projection on the basis of the orthogonal eigenvectors. Okay, that will allow you to obtain your system of uncoupled scalar linear second order ODEs, which you learn to solve in differential equation. And you have a chance to review in my extra lectures in this course. Okay, so we have the scalar equations. And then once you solve the scalar equations, that's the previous slide, then you can recombine to obtain the final solution of the whole system. Okay, like I said, the same methodology applies when you deal with millions of coupled equations in real world industrial part. Okay. So that, and then towards the after I discuss the Beatles and the detection of the opening chord, I will also, in parallel, introduce the physics of musical instruments. Basically, this is acoustics and vibration. Okay, engineering, acoustic, and vibration. With music, story as a background, because that's enlivened. The topic. Everyone likes music. Is there anyone who doesn't like music? Life would be quite boring, right? And this is also connected to Richard Feynman's letter to his piano tuner. You will understand the letter by Richard Feynman, and when you understand it, it's beautiful. I saw this paper back in 2009 but I didn't understand anything. In his letter to his piano tuner, I learned a lot teaching this course last semester. Okay, I found the article in 2009, but the paper by the mathematician, Canadian mathematician of 2004, that get me into introducing the topic of the Beatles and the detection of the opening chord. I developed my knowledge in music theory, and when I read back the letter by Feynman, I understood everything, and I hope you enjoy that letter. It's not easy, but it's when you pass the hurdle, it's quite enjoyable. Okay. So that involves solution of PDEs, the wave equations, and so on. We'll have more time to talk about that. Okay. Let's see. Maybe for the time that is left, let me see whether. Yeah, so you get into Sakai. This is the portal. You can click at the portal, and you see what I showed there. There's already a few students looking at the portal. Yes.
Can you discuss how the grading for this class works, like the in-class assignments for more important? I'm just trying to find it online.
In-class assignment, don't worry about that now. We'll get there. Yes. Yeah. It's basically I have a form that people sign. That's probably the easiest part, the in-class assignment. So, but I want to show you for the remaining time this video. This is the integrated product and process design video. You can go to this link here. Let me zoom in so that all of you can see. Let's see fit here. So the integrated product and process design course is they have installed for me. They probably forgot to install one software, but I hope just focus on this. Forget the detail. It's a 2-semester sequence that replaces your senior design and one elective course, like I mentioned. And this is a video that was created by my team, and so I want to show this video to motivate class. basically, the goal of this project was to replace explosive device to deploy satellite by non-explosive method. But there are many other types of projects, from bioengineering to many other types that you can select. Okay, so keep this in mind. We'll meet again